Hi folks, today I'm going to be talking about this object which is currently seen on stereo behind Cor2. This is Venus, but Thor News has done a couple videos about it today, wondering first what it was, and once finding out it was Venus, he's wondering why is it so high in the image, why does it have what appears to be a tail, this spike coming down here, and why does it appear to have what he describes as wings, these horizontal lines which pop up. So to answer these questions, I looked at the raw image data, which you can get off of the stereo website FTP, as opposed to the processed image data, which you see here. This image taken at 8:24 Universal Time on May 28th, and you can see the spike coming off Venus and the beginnings of what he describes as the wings. They're not terribly obvious in this particular image, but when you look at the raw data, you find out that the quote-unquote wings are actually one of the more obvious features, and the spike can't really be seen at all. This is the raw image data for that very same image. Now this is just the beacon image data. That's what we get from the spacecraft first, or beacon images. Those are downloaded in near real time and presented to us. They're downloaded both by professional and amateur stations. The full image data won't come for a few more days. That has to be downloaded by the Deep Space Network. It's done at a slower cadence. The files are much larger and take longer to download. So this is the beacon image data from 8:24 Universal Time, and you can see what he describes as the wings here quite clearly. Now, what this is actually CCD blooming. Venus is a very bright planet. In fact, it's the brightest planet in our sky. It outshines even Jupiter when it's at its brightest. And as a result, it actually overfills the pixel columns. And when it does that, the electrons start to spill into neighboring wells, and you get what we call CCD blooming. Now you can see this more obviously in this image from 2009. You can see the detail better. That's because this is the full image data that was downloaded, not just the beacon image data. And you can see quite clearly the blooming forms these very sharp lines that are only 1 pixel wide apiece, and it forms these columns. In this case we have about 3 columns that are neighboring each other directly, and it looks like one solid pair of, I guess you could call it wings, but it's really just CCD blooming. It's because Venus is so bright. Like I said, it's overfilling those pixels on the columns where Venus is and spilling over into neighboring pixels on the same column. The columns are arranged horizontally in this case, so it forms horizontal lines. You can see the same effect on Mercury, just to a lesser extent. Mercury is also quite bright because it's a planet, not a star or faint detail in the corona, and as a result it starts to overfill the columns as well, just to a much lesser extent. Now the other thing that we saw in the images were these linear spikes, what he called the tail. This is actually a diffraction spike. You can start to see it here a little bit in the raw image of this image from 2009. You can't really see it at all in the image that was taken at 8:24 earlier on May 28th this year, but you can see, as I said, the CCD blooming, and if we do a dramatic amount of contrast enhancement similar to what NASA does, we can finally see the spike. It's quite a faint detail. The contrast enhancement that NASA does tends to make it difficult to tell just how much dimmer the spike actually is compared to Venus. It looks like in parts it's as bright as Venus itself, but in truth it's actually much, much dimmer. And Venus itself is not nearly as big in the image in the raw data as you might think from looking at the JPEG. The JPEG version is so enhanced that even faint halos around Venus from optical distortions are completely blown out to the point that they look solid white. In truth, you can't even see them at all in the raw image before you do some processing on it. You can start to see it after you do the processing that I did. You can see a little bit of a halo surrounding Venus, and once you do as much contrast enhancement as NASA does, this becomes completely blown out to form the full size of Venus in their version of the image. Now in the image from 2009, we can see some additional detail in the halos that surround Venus and Mercury, and you can tell that these are quite clearly transparent optical distortions, not actual physical manifestations. The diffraction spike, you can see just how big it is in the processed version. You couldn't really see that in the raw version, but once you do all the processing once again, you can see just how big this diffraction spike is. And once again, in their version of the image, it tends to, again, exaggerate just how bright that distortion is. It looks just as bright as Venus itself. In fact, it's much dimmer. You can also see an identical but smaller diffraction spike present in Mercury. In fact, it's parallel to the diffraction spike present in Venus. It's because it's determined by the optical configuration of the Cor2 imager. The Cor2 imager is a coronagraph with a occulting disk and a occulting holder bar that attaches to the disk, and that produces these diffraction spikes in bright objects. Now, the other question, the reason why it's so high in the image, that's just a function of Venus's orbit. Venus, in this case, as of today or yesterday, as when this image was taken, its heliocentric ecliptic latitude is about 1.5 degrees, a little more than that. Now, obviously, it's more than 1.5 degrees above the position of the Sun, which is itself about half a degree in size as seen from stereo, just like as it's seen from Earth. Stereo behind is about at the same distance that Earth is on average, and so the Sun is about half a degree wide. And you can see the Sun is approximately the same size as this white circle here on the processed JPEG version of the image. And you can see that it's quite a good distance from Venus, quite a good distance below Venus, more than 1.5 degrees. But that's because it's the heliocentric ecliptic coordinates, about 1.5 degrees positive latitude. Now, it's also about 3/4 of an astronomical unit away from the Sun, whereas it's only about 1/4 of an astronomical unit away from stereo behind. And as a result, if you do the math on that, if you do the trigonometry, you'll find out that it should be about 3.6 degrees away from the Sun, above the Sun, as seen from stereo behind. And if you measure the distance from the center of the Sun, in the center of this white circle, to Venus in the image, you'll find that it's about 3.6 degrees away. So, indeed, Venus should be that high in the image. It's just a function of where it is in its orbit. Venus does not orbit perfectly on the ecliptic. It has a little bit of inclination to it, so it will be above and below the ecliptic. And because Venus is on the near side of the Sun, in this case, relative to stereo behind, and because it's much closer to stereo behind than it is to the Sun, it's actually a good distance above the Sun. In fact, I predicted that this was going to happen, that it was going to pass very close to the top of the image. I predicted this months ago. But I wasn't even sure if it would be within the field of view. That's how close it was. And indeed, you can see it's writing right at the top of the field of view. That's expected. It's just a function of the orbit of Venus relative to the orbit of stereo behind. Now, if it were on the far side of the Sun, on the opposite side of the Sun, it would naturally be much closer to the Sun in the image. The distance between the Sun and Venus vertically is somewhat exaggerated by the fact that Venus, in this case, is about 3 times as close to stereo behind as it is to the Sun. So, there you have it. That pretty much covers everything, and I hope with that you have a nice day.